Mike here, working with the refrigerator here again. It's been a couple of weeks since I've done a video on it. Simplified things here a little bit. We're back to the old static condenser from the thermosiphon we were working with before. The thermosiphon worked with the static condenser, but I wasn't really too impressed with the overall performance of it. Didn't seem like something I wanted to pursue much more. Proved the concept, everything worked as I more or less intended it, but subcooling was a huge issue and it just didn't seem like something worth pursuing. So we're just going to keep things simple, go back to the basic static condenser. So this is more or less how it stood several weeks ago. We just have the static condenser and no subcooling loop really. Subcooling is still kind of an issue, and then it drains into the filter dryer and the capillary tube. Overall, if you haven't seen any of these videos before, we have a propane refrigerator. That is propane refrigerant vapor compression system mounted into an existing mini fridge to use as an insulated box. About a 1/10 horsepower compressor, 120 volt AC, discharges up into the static condenser, drains into the filter dryer, 10 feet of 0.26 inside diameter capillary tube. We do have a heat interchanger there, about 3 feet of the capillary tube around the suction line. Goes down into the box. We have a stainless steel pan there with a mixture of propylene glycol and water, about 10% propylene glycol. Starts to freeze at about 26 degrees. There's just a copper loop in there. And then the suction line comes back up. Like I said, the heat interchanger there loops up around and then back into the compressor. There's a series of thermocouples throughout the system. Discharge superheat, very important. Then we have subcooling, important. We have one directly after the evaporator. I can't see it all that well, but it's up in there. And then we have a fourth important one, which is after the heat interchanger and the suction line, right before it goes into the compressor. In addition to that, we've added some pressure transducers. We have two of them, one on the high side and then one here on the low side. Those things output 0.5 volt DC to 4.5 volt DC with a 5 volt DC input. Those are wired right into the Zoom box temperature logger where all the thermocouples are installed. We have 8 thermocouples, so we're also taking temperatures like ambient temperature, box temperature, a couple different places, the propylene glycol, non-eutectic solution. So I want to talk about some of my observations and some of my plans here for the near future. What you're looking at here is about 5 hours or so of data. Most of the run times here that you can see are pretty similar, so I just picked this one because it's a pretty commonly looking one. Run times usually somewhere about an hour and a half run time, and then off time is usually somewhere between about 4 to 9 hours, depending on ambient conditions. The warmer it is, the shorter the off time. So one of the first things I wanted to point out here is that we have some new information here. Before we had just the temperatures, which are the all these color lines above. Now we have voltages here too, so that's the pressure transducer. Here's the high side pressure, here's the low side pressure for a run. So you can see they were at equilibrium, and then the low side drops and the high side of course rises during the entire run. Whenever the thing shuts off, we go back into equilibrium over the course of a couple of minutes or something like that till the high side pressure drops. Just to begin with, I'd like to just point out that to understand the start of this, you have to understand kind of the end of the last cycle. During the last cycle, at the end of this one, since this one looks like any other one, we had some liquid refrigerant that's built up into the high side, and whenever the compressor shuts off, that liquid plug is pushed into the low side. So, we have probably a good bit of migration of the liquid refrigerant into the low side. Also, the low side's cold as well, so even during that off time, a lot of vapor is going to end up condensing into that low side. So probably the majority of the liquid refrigerant is in the low side at the startup. So whenever the thermostat calls for cooling, right now it calls for it at 27 degrees with a thermocouple mounted to the bottom of the pan, and then it shuts off at 13 degrees. That seems to work relatively well right now, but I'll, get that a little bit tighter here, figure out what an appropriate setting for that is. So whenever the machine first kicks on, obviously the high side pressure starts to rise a bit and the low, drops off rather rapidly. We get this downward spike. These are the superheats, the one before and after the heat interchanger. The red one is interesting because it drops pretty suddenly. The blue one drops a little bit. That's after the heat interchanger. Of course, it's going to be a little bit warmer because you have the cap tube wrapped around it. It's in an ambient environment, so it's going to be warmer anyway. Probably because the pressure drops so suddenly, the what liquid is in there starts to boil off quite rapidly and cools those thermocouples. Then you see a rather sudden rise again in the temperature of both of those, more noticeable in the one after the heat interchanger that's in the ambient environment here. Probably because, again, you have that capillary tube wrapped around it. The reason it rises so rapidly probably has a lot to do with the fact that once the temperature drops really quickly, we get a heat flux from the copper tubing that's encasing all that refrigerant. So it starts to warm it and ultimately superheat it. Takes a little bit of time until the pressure in the high side rises to the point where we regain our liquid plug that we lost during the off time. We have a fixed bore capillary tube, so it doesn't have really any control other than just kind of the natural characteristics of a capillary tube in a refrigeration system. This refrigerator is very similar in construction. I mean, it doesn't appear similar to most refrigerators, but the vapor compression system is more or less designed in the same fashion as any normal refrigerator. It's going to have a heat interchanger like that with the cap tube wrapped around the suction line for a couple of reasons, but probably the most important is it prevents any liquid from slugging back to the compressor. I'm not sure if I'm going to keep the heat interchanger. I'm going to mess around with some different things, but whenever that suction superheat is so high, we end up with a rarefied gas, superheated gas going back to the compressor. And that's really bad for the volumetric efficiency of the compressor. For each intake stroke, suction stroke with the compressor, it draws in less gas, less massive gas, and then discharges less massive gas, as opposed to if it had like a more saturated vapor, less superheated vapor, denser. So, we have kind of limited volumetric efficiency there and limited mass flow through the compressor. So even though the pressure is rising in the high side, it's not pushing a whole lot of mass, relatively speaking, into the high side to eventually get the temperature up and regain that liquid plug, by condensing that warm vapor. In addition to that, you also have the fact that the liquid around the copper tubing is a bit warmer, and it's going to flash off a lot of that refrigerant pretty quickly. So we end up with a superheated condition in the suction line. And then, like I said, with that cap tube wrapped around with the heat interchanger, the actual gas temperature that the intake is getting on the compressor is a bit warmer because it's cooling down that warm gas that's passing through the cap tube. The other limiting factor is the cap tube itself in startup, because we're just passing gas mostly through it. We're not getting any condensation right off the bat. Cap tube doesn't really pass gas all that well, so you kind of get this choked flow in the cap tube. And liquid flows a lot better through a cap tube. So we're not feeding the evaporator sufficiently for the heat load that's kind of required. So we have that reduced mass flow rate at the cap tube as well. So this goes on for about a half an hour until things kind of get in the groove, we'll say. One of the next interesting points is about the peak of the superheat on the blue line there, the one right before the compressor. I'd point that out because almost in every example it seems to correspond with these two lines up here and a change that occurs. The yellow line that flattens off right there, that's subcooling after the condenser. The blue one is discharged superheat. And you can see they more or less track one another until about this point here where they separate. I think that is probably the point where we're starting to get a liquid plug on the cap tube, and we're actually getting some condensation. Before this point, it's probably mostly just gas passing, by the superheat thermocouple and the subcooling thermocouple, and that's probably why they're the same. From then on, we're probably actually getting some condensation occurring, which is going to leave a liquid plug at the cap tube. We're going to get more mass flow into the low side, which is going to better feed the low side. and correspondingly we also see a slight drop in suction temperature there right after the evaporator. And also we start to make a little bit of headway on the one after the heat interchanger, because before this time it's adding heat. Well, it's adding heat to the at the heat interchanger all the time. Capillary tube is being cooled down, but we're actually starting to kind of get ahead of it a little bit and get a little bit less superheat on the suction line, a little less rarefied gas, more dense gas going into the suction valve, and a little bit better mass flow rate through the compressor, and then correspondingly through the cap tube as well. So I think that's an important point to point out. Kind of the next interesting spot here is where the suction superheat after the evaporator finally more or less bottoms out. And just from observation and from kind of just common sense of looking at it, you can see this kind of flattens out and slowly drops. It's pretty much come down to saturation there at that point. Also, right around that point in time, you see a change in the slope on the suction superheat after the heat interchanger as well. Things starting to change, and then you have this sudden drop off in the suction superheat before the evaporator, post heat interchanger. Some different ideas on what's actually occurring there. That might be the point where we started to gain a liquid plug back here, and at this point we still have some choked flow, some gas passing through the cap tube, and finally at that point we're getting good flow, and we have a nice solid liquid plug there. But again, I'm not sure. I have some different theories on that. Beyond that point, even with the heat interchanger, suction superheat before the compressor is still only 1 to 3 degrees higher than saturation. So we're doing pretty well there. In all likeliness, we're actually passing some liquid through that heat interchanger, which is being flashed off by the heat interchanger. Another interesting point to talk about here is kind of the peak of the pressure on the high side. That seems to occur at an interesting point there where it finally peaks and then it kind of drops off and slowly drops over time. All this time here, from the beginning of the startup until probably about that point, we were getting plenty of kind of back pressure from the gas that's trying to pass through the capillary tube. Somewhere in here we're getting pretty good flow, and that's allowing more mass to flow through the capillary tube and relieve some of that high side pressure. Also seems to kind of correspond to the subcooling temperature, because if you have a drop in high side pressure, all other things being equal, subcooling temperature is going to drop accordingly. If you have, say, a 10-degree temperature difference between ambient air and your saturation condensation temperature, and then my subcooling is pretty piss poor. It's usually like 7 to 10 degrees, below that. So, those two lines kind of track together relatively well. Once we finally reach close to saturation on the suction line, we're getting better mass flow rate through the compressor. We're getting better mass flow rate through the capillary tube. Everything's running, pretty swimmingly. We'll just get a drop in the superheat, the discharge superheat up there. See, kind of slowly falls off there a little bit, and I think that has a lot to do with the fact that the compressor is getting better cooling from the suction line. That's how a compressor like this gets cooled, by the suction vapor, until we finally get to the point where the thermostat is satisfied. And excuse me, I'll take a swig of beer. And compressor kicks off and everything goes back to equilibrium. So that's kind of a summary of what I think's going on in here. There's a lot of other interesting points I'd like to make, but that'll make this video far too long, and I've tried that, and it doesn't go very well. So what I'd like to do is to reduce this first half here. This we're getting actual real cooling that's occurring in there, but I'd like to get down as close to saturation as quickly as possible in the run, to gain that liquid plug rather rapidly. Something else I wanted to point out, and I forgot about this. This is pretty important. One of the things that changes during this run cycle, apart from everything, is the conditions that the evaporator is in. How effectively the evaporator conducts heat into the refrigerant in the evaporator is not a constant by any means. At the beginning of the run, assume that it has a lot of liquid around it that was melted off from ice during the previous off cycle. So there's plenty of heat load to be had right there in the immediate surroundings of the copper tubing. And that's why in the very beginning we get that, yes, we get the sudden drop in suction line temperature, but then it quickly rises again. Evaporator has a lot of work to do, and for a given amount of mass flow rate entering into the evaporator, it might not be sufficient to actually properly feed it. One of the reasons why we're getting higher superheats there on the suction line, apart from the warm gas passing from the capillary tube. But then, of course, over time, it is still doing some cooling. I mean, it's definitely dropping in temperature. There's no doubt about that. It's just not as efficient of a process as I would prefer, because that water is going to start to freeze back to ice. It's going to form an insulative barrier around the copper tubing, and so the thermal conductivity across this layer of ice and into the copper tubing, into the refrigerant, is going to be reduced. It's going to form this insulative layer that, as it grows larger and larger and larger, the liquid refrigerant in the low side is going to become less. There's going to be less of a violent boiling occurring. So that given say a given amount of flow of liquid refrigerant into the evaporator at the beginning of the cycle, it might not be enough, but towards the end of the cycle, or towards the middle, we'll say, it might be plenty, because the capacity, I suppose the capacity of the evaporator has been somewhat diminished. So I don't know how well I explain that, but it's not necessarily a good thing. But in the grand scheme of things, I can work around it. And if I decide I want to pursue the whole propylene glycol water thing, beyond designing better heat exchangers and just a better evaporator overall, it's something I'm going to have to deal with. Okay. So what can I do to improve this? Well, one thought is an accumulator on the low side. I've dealt with accumulators a bit before. I don't know how well I was understanding the process, but over the course of the last few weeks, I've really been paying close attention with the addition of some of the pressure information, trying to better understand exactly what's going on in every one of these cycles. To me, what the accumulator does after the evaporator is it allows for some variation in system conditions. So depending on ambient environment temperature, maybe it's 60 degrees and it's cool in the room, maybe it's 90 degrees in the room, and then from the beginning of the cycle to the end of the cycle. So if this system as it stands right now, if I were to add some extra refrigerant charge to it, I could get this to drop to saturation much more quickly. However, it's going to raise the head pressure as well. Because at certain points in the runtime, that liquid is eventually going to start to back up into the high side, and I might get a little bit better subcooling, relatively speaking. But the head pressure has risen as well, so the condensation pressure has risen in the high side. So I haven't really done myself any service. Eventually, that head pressure rises and forces more liquid through the capillary tube and better supplies the evaporator, but I have to think about overall system performance and amperage draw on the compressor and discharge superheat and things like that. So say for instance in low ambient conditions, the head pressure is going to have to build and build and build and develop a pretty hefty liquid plug behind the capillary tube until the pressure rises enough that it's really effectively condensing liquid. So you're going to have this liquid that's going to back up into the high side. And conversely, in really high ambient conditions, when it's rather hot,
it's the high side pressure is going to be pretty high anyway, and it's really going to be rocketing a lot of refrigerant through to the low side. So I guess the point I'm trying to make is you need to have some place for that liquid to go, and then, that's a tank of some sort, an accumulator. In those conditions where that liquid's backing up into the high side, we don't want to starve the evaporator. So if the low side liquid is only stored in the coil itself, and a lot of that liquid's backing up into the high side, the coil gets kind of starved, and we end up kind of superheating that gas. We don't really want to do that. We want it to operate in such a way that at all times the evaporator is pretty much well fed. Sometimes it's overfed, and in which case a liquid can accumulate in the accumulator, and at other times the accumulator can be more or less empty, and the evaporator is still properly fed, and we're getting that saturated vapor, that dense vapor, back to the compressor. So in addition to that, I want to get better subcooling on the high side. So I need to add some more heat exchange area there, and possibly a receiver there, and balance these things together. Beyond that, when we first start up here, although we have still pretty high superheats right after the evaporator, this red line, relative to saturation temperature, which this is pretty much where that's at right there. You can see that the superheated gas finally going to the intake valve and the compressor is probably, that much double in temperature. So it's a very rarefied gas, and that's due to the heat interchanger there and all the heat being added by the capillary tube. We can install a heat interchanger like I did, not only for the purpose of trying to protect the compressor from a slugging condition where it's pulling liquid back, but we also have to consider the possibility that we can pretty much bypass some of that heat energy that wasn't dissipated properly in a subcooling fashion in the condenser. We can kind of bypass the evaporator and go straight to the compressor with that enthalpy to be dissipated, again in the condenser, rather than just flash that off either in the capillary tube, which creates choked flow and we have reduced mass flow rate, or spitting that warm gas into the evaporator where it eventually has to pass back to the compressor anyway. So it's kind of a nifty way to transfer some heat and bypass the evaporator. However, I think the drawback of it is, the initial pull down, getting into equilibrium, takes longer. And I'd like to experiment with removing that heat interchanger, or at least removing maybe 2/3 of it and going down to about 1 foot of capillary tubing, just to provide myself a little bit of protection against slugging back to the compressor, and see how it overall affects the performance here. That's probably one of the first things I'm going to do. Actually, one of the first things I'm going to do is add a little more refrigerant and see how that affects the shape and length of time that this horn exists in. And then longer term projects, when I get into metal spinning, are going to be making an accumulator, and then adding some more subcooling surface area to the condenser. Possibly adding, do these things in steps, one at a time. Adding some evaporator surface area. I wanted to modify things in there a little bit, and eventually, from what I learned from this, some of these steps, I want to apply to making another ejector. And there's a whole playlist on ejectors that I did last summer. It was a lot of fun. Didn't really produce anything all that practical, but demonstrated that the principle works. And I'd like to apply what I learned with metal spinning to make a much better quality ejector that to me holds a lot of possibilities for getting the system into good level operating conditions. Basically getting that liquid plug as fast as I can by getting low suction temperatures to the compressor as quickly as I can. So increase the mass flow rate to the compressor so I can gain that liquid plug fast, get good mass flow through the capillary tube so I can properly feed the evaporator earlier in the run, rather than kind of having to wait until the conditions of the evaporator change in that all this ice forms around the tubing, kind of reducing the necessary liquid supply from the low side. So I don't know how much of that made any sense, but I've tried this video a few times over the last few nights, and this is about as far as I've gotten. So I'm just going to go ahead and end it there and finish drinking my beer and probably have another one. So if anybody's interested in the pressure transducers, I can talk about those a little more in the future, or just comment or send me an email or something like that. Right now I'm just set up, I just have 0 to 5 volt displayed on there. Not all that concerned about what the actual values are. I'm not sure if they're linear or what the relationship is, but that's something I'm going to figure out here in the long run. Yeah, I suppose that's about it for now. Bought a lathe, haven't got it out of the box yet, so I need to rearrange the shop a little bit, get that set up, and make myself some metal spinning tools. So thanks for watching. Hey, I did it!